Yeah, so we saw different operations on finite state machines, like combining different finite state automata or transducers. It's like union. A union means you are applying an or operation, that either this or this, both the sequences are acceptable. Then concatenation means this followed by this, right? So X followed by Y is accepted by A concatenation with A concatenated with B. Then we saw epsilon symbols are dummy symbols. Basically, when you say input is nothing or output is nothing, then you use an epsilon sign there. Closure means you are looping in and you're saying that this whole thing can be repeated either 0 or more times or 1 or more times. These are two common kinds of repetitions. And then you have intersections. Intersections are essentially X and Y. Sorry, means X is accepted by A as well as B. Then X is accepted by A intersection B. Then we saw determination and minimization. Determination means your from each state, if you get an input, then only single path is possible. Like this is non-deterministic, because if you are in this state and you see the input I, then you don't know which one to go. So basically you have to send your tokens down both the paths. So this is a non-deterministic FSM, whereas in deterministic FSM like this, you will have only single path to be taken. So when you see I, then there is only one arc which accepts I as the input. And then we saw composition, which is basically for transducers, that you output of one becomes the input of the next. So output of A becomes the input of B. And we saw the power of this finite state machines to model different things, like different formats. And then we use uh, composition to basically convert or basically uh, break down your symbols further and further. Like you phone number is broken down into area codes, prefix, suffix, etc. And then the each of these, like area code is broken down into 0512, prefix is broken down into 259 or 679, etc. And so then you can make further uh, finite state machines which break down zero into, let's say, phonemes z, e, r, o, and then you can further break down phonemes into um, tri-states, right? Three states. So, and then you simply use your composition operation to make the whole graph, which will accept the acoustic input as the input, and output will be your, let's say, the phone number, just the phone number. Or maybe it could be a name also, right? A particular person, he has a particular phone number, so that particular phone number will map to that particular name. So you can make that as well. Now, okay. Yeah, then we saw, okay, how do we implement FSA using FST? These are all easy stuff. Now, okay, then we came to weights. What are weights? Basically, so when you are passing your tokens, then all paths may not be equivalent. For example, you may take multiple paths and each path has got a weight, and you can choose, uh, let's say, the path with the least weight or with the maximum weight, and that is your final path. And you can see the hints towards Viterbi algorithm, that in Viterbi we have different paths, but we also have weights associated with each transition to say that how likely is that path, right? And then we discussed the concept of graphs, that how general graph problems can be represented using finite state machines. We took the example of Google search, right? You have different locations, they are the nodes, and then different arcs are carrying the information of different paths connecting those locations. And let's say you want to find the shortest path to go from location 1 to location 2, or else you want to find the path with the least traffic. So these weights will change when the traffic changes, let's say. So these weights contain both the factors, the distance factor as well as the uh, traffic factor. Basically, when the traffic is more, you can increase this weight. Traffic is less, you can decrease this weight. So that finally, your actually the thing is that this finite state machines is automating the entire thing, automating because the same program or the same framework can be used for so many problems, whether it is speech recognition or finding the routes on the Google map, etc., etc. So the same abstract structure or the graphs or finite can be modeled with finite state machines. Yeah, and yeah, so then we just briefly saw that Vitab includes finding the path with the minimum weight, or let's say finding three best path with the minimum weights. So let's say the weight on one path is the minimum, then second minimum, then the third minimum, or in the increasing order. So this is what is our these are finite state machines. Now we want to apply them to automatic speech recognition problem. So how do we do that? In automatic speech recognition, this is the problem. We are given acoustic features, let's say MFCC features for your sake of understanding, but it could be any acoustic features. And then you ultimately want to obtain sequence of words or maybe sentences as your output. Let's say one sentence is the output. Now, how do we reach to that level? So, okay, so probability of W given O, I don't have a model for this, but I can use a Bayesian formulation, the Bayes rule, to convert it into O given W times W and argmax over W, right? So denominator can be ignored. Now, P of O given W is modeled using finite state transducers, and P of W is simply the grammar. Basically, it is giving you what is the probability of this sequence of words. Let's say you have a sentence, I am eating, and you will say this has got a high probability, but another sentence, I am, let's say, doing something else. What? Uh, I am, what? I am roaming something. I'm roaming. That is very less probability because given the COVID time, nobody would like to roam around. So roaming has very low probability. While I am eating will have a high probability. Similarly, let's say there is a grammatically wrong sentence. I am eating versus I are eating, or I is eating. So both I are eating and I is eating will have very small probability, while I am eating will have a larger probability. So like that, this can model words, and then coming to this part, you further break it down into O given distribution. O given synons. We saw that these are synons, or the states of your phoneme, and then probability of states given the phoneme, probability of phoneme given the word, and then you obtain this final thing by summing over all these extra variables you have introduced. But of course, this sum is very sparse, right? Like, let's say if I have a phoneme, how do I say? No, let's come to this one. The words. Let's say here I have, it's very sparse. Like, let's say the word is cat, then cat is made of k and t. There is no question of having a s sound in cat, right? So those, it will have very less probability, or maybe close to zero probability. So basically this is a very sparse thing. So that's why, okay, let's see now how to implement all these sparse things in a very efficient way. Because if I have to compute probability of so many phonemes given a single word, then that is very inefficient. But using the finite state transducer architecture, I can make this sparse computation also very efficient. Okay, so let's begin with Viterbi algorithm. Do you remember what is Viterbi algorithm? Okay, let me give a quick recap of Viterbi algorithm, which is required for this today's discussion. I have to pick one example for Viterbi. What do I take? Okay, maybe let's take an example. The word is Hari. So you have the word Hari, and so what do you have? Hari is very long word. Let me take a short word. Let's say just her followed by a, or let's say two. Two is a valid word. Two, T W O, two. So basically, it means your phonemes are, let's say, starting today's discussion, we have two. This is the word, right? And this is basically composed of t followed by u, two. These are the phonemes, right? So how does my uh, okay. So how does my what do you say, finite state machine look like? So this finite state machine models this part: probability of phonemes given W or W given phonemes. They are both equivalent. Uh, let's say we are modeling probability of uh, what is it? P given W, phonemes given word. Oh, but actually, in the automatic speech recognition problem, we want to go from phonemes to words because the output is the word, right? So we will model probability of W given P. W given P. Of course, you know these are interconvertible. You can just use Bayes rule to get P given W. Uh, but okay, let's say we want to model probability of word given P. Then this will be input is the input is the phoneme and output is the words. Okay, you have a starting state. You go to, let's say the word is two, so the input is t, output is two, or then the input is u, output is nothing, and then you reach the final state. This is your starting state, this is your final state. That's it. So you can represent it in two ways. One is this, where the this is in the beginning, or the other method is you have the same thing and you put this at the end. Both are equivalent, right? So you have it here. So input and output are the output can be either in the beginning or in the end, doesn't matter. So generally this is preferred. Why? Because you know when you have multiple words, then you may, like, let's say, how do you represent multiple words? So a dictionary. Uh, just give me a second. Turn on this. Okay. How do you represent a dictionary? Okay. So we are discussing this part, right? And then suddenly dictionary. How do we represent dictionary? Let's say in my dictionary I have all these words. I think I'm taking an example which you have in your project: 1 2 3 4, all these digits. So let's say I have one. So one will map to some sequence of phonemes. Let's say na. I'm not writing the IPA notation, just some easy to understand notation which you are all familiar with. Two will be just two. Three will be just. Th is one phoneme, r, and then e. Three. Okay, there are three phonemes: one, two, and three. Three. If you see in Hindi, it's something like this: three. There are three phonemes: tha, ra, and e. So actually, if you want to see how many phonemes are there, then if you know the Hindi spellings or Hindi alphabets, then you can very easily see how many phonemes are there. From English, it is difficult to tell because there are 5 letters here and there are only 3 phonemes actually. So and here you have 3 characters and 3 phonemes. So from English you cannot tell directly, but if you have, let's say Hindi, in Hindi it would be one. I don't know. Va, one, one, one. So va is one. Means va is first. A is second. Na is third. One. Similarly, two. You have, let's say, two. Ta is first and u is second. Because it is equal to ta plus u. This is va plus a plus na. One. So actually, there is halant because there is no so it's not vana, it's van, one. Vana would have been 4 phonemes. Okay, so anyways, that was just a side thing. How do we find these phonemes? Okay, now let us say I have to take some example where we have similar, let's say 6 and 7. Is C, E, X, and 7 is S, A, V, 7. So, okay, 7 has a different story. I will discuss with you a little later. 7. This is double A. 1 versus 7. And A. 7, 1, 1, 1. It could be single A also. Okay. Anyways, both the possibilities are there, but let's stick to this one first. Now, when you will form your FST, then it will be something like this. Let me take only these 3 examples just for sake of time. You have it like this. You have output is nothing. Here it is 3, right? And then the final state. Or it could be sa, e, and then x, 6. This is 6. And then you have 7. Sorry. 7. Right? Now you see, this is your union. So you have different words, W1, comma W2, comma W3. And what you are doing is, you are taking a union of all these words, union, and then you can repeat the words. Like, so for example, I have told you that only 3 words are possible in a row. Then you will say, okay, let us say this is why this thing. So you will say u of w1 so on, followed by again a union of w1 so on, and again followed by a union of w1. So this is your FST, which will output 3 words or 3 digits, right? The output will be just 3 digits. So this is what you can use for your project. But in practical life, let us say you want to repeat them multiple times, then you can simply say UW1 so on, then a star. So any of these are possible, but for your project, I think you will be using this kind of a finite state machine. So basically you construct W1 and what is it? The word 1, word 2, word 3 in this way. I hope it is clear. And if you make it deterministic, okay, now you have to make it deterministic. To make it deterministic, this union thing, so after doing union, you will do some determinism so that there is single going. Let's say it will become like this. So, let me, it will be, you will be kind of merging the two. something like this, blank blank, right? So either 6 or 7. Now there could be weights also associated with these. What are the weights? Let us say, okay. Now let me tell you here why I said 7 could be a case. I could pronounce it in two different ways. It could be either 7 or 7. 7 means I'm not uttering this, so it is se 7. 7. Both are possible. Now, so in the trellis also you will get both. In the HMM topology also you will get both. But you can use some weights to say which one is more common in a particular language. Let's say in Hindi, I think nobody will say 7. Mostly people will say 7, right? In India. But in West, nobody will say 7. They may say 7. So uh, the weights may be different in different locales or different locations, but the basic idea is that you can use weights to control which is the preferred form of speaking. I think here we missed P of W. Did we cover P of W? No. Yeah, this term P of W. How do we model P of W? P of W is simply what do I do? Blue. This is called the grammar. What does that mean? It tells you sequence of words possible. Let's say if I say I am sorry eating. Right? I can also say I or they are eating. I can also say I am roaming, or I can say I am what do you say? I am um, eating, roaming, or sleeping. Now you can give weights and say, okay, I am roaming is very less probable, and eating is more probable. So roaming will have a higher weight, and eating and sleeping will have a lower weight because we want to take the trellis or the path which has the minimum weight. Start state. Okay, so basically this is how you represent grammar. Now this kind of a grammar is called a finite state grammar because there are finite number of states. But actually you know that um, I can construct I can use composition and I can construct potentially infinite number of sentences or given a finite number of words, right? I can say uh, I am eating because they are roaming. Like I can construct so much. Like I am eating an apple because they are roaming uh, in the city, something. So basically, finite state grammars may not be able to capture much variation in the language in terms of compositionality, right? So we have to bring in some other kinds of grammars, let's say context free grammar. So I can have context free grammar or context dependent grammar. So the idea is that you can expand it. Let us say you will say, I am eating, or I am almost finished with my eating, or I am almost finished to describe how I am eating. Like you can, this basically it defines some set of rules by which you can use compositionality to expand your sentences. But then, how do you make context-free grammars? You can use closures, and you can approximate them with finite state grammars and closures, etc. So basically, you can still approximate them with finite state machines. And another kind of grammars which is very popular or the most popular in this what do you say in speech recognition literature is called n-gram based grammar. So n-gram grammar. So in n-gram grammar, what do you say? You try to model a sentence as sequences of n different words. Let us say n different words. Let us say a big sentences. For example, I will be teaching today morning. Right. So there is some sentence. So let us take 2 gram or 3 gram. Let us take a 3 gram, a trigram. So what does it mean? It will extract all the triplets from the sentences. I will be is one triplet. Will be teaching is another triplet. Be teaching today is another triplet. Teaching today morning is another triplet. All these triplets can be taken and they can be kind of saved. And I will say only these triplets are allowed. So I am constraining only triplets. My constraints are only on triplets and not on the entire sentence. So you see the power of this triplet based grammar is that you can construct very meaningful sentences, um, and it is not very difficult to track also, because a sentence can have so much of variation but triplets will have relatively less number of variations, right? For example, if you have got 100 words in your lexicon, then here you will have 100 words, here let's say 99 or 100 words, here again of the order of 100 words, so only 10 to the power 6 possibilities are there, whereas in a sentence there are so many possibilities. So it means you are trying to reduce your or basically trying to capture as much variation as possible but still while minimizing your computations. So this is n-gram based grammar. And yeah, there are some provisions, like if you see a word which is not there in the sentence. Let's say in my training, I never see a sentence like, I will be only teaching today morning. Let's say, so will be only is not there in my training set. Right? There is possibility that some triplets are not there. Then you will use a dummy triplet or a dummy state, which contains basically when you which you use to model unseen data. That is called the back off state, a back off state. Anyways, that is just some details. When you see this word, don't get frightened. This is just a back off state or back off word, whatever. So basically it is just a dummy, or it's a kind of umbrella word which is used to model or all unseen words or unseen states. Okay, so I think with that much, let us proceed. So we have discussed P of W, how we model P of W using FSMs, and then how do we model P of W given P using the FSMs. Now I want to, let us go back to this. Yeah, so P of W is done, P of P given W is done, P of D given P. So the input is the synons and the output is the phonemes. This is called P of P given D. Right? D is the synons, P is the phonemes. So how do we model P of P given W? So the thing is, I know every phoneme. Let's say k is made up of k1, k2, k3, right? I'm splitting each phoneme into three synonyms or three states. I use three states to model each phoneme. Um, it's very okay. Let me just, before we move on, let me come back to our example of um, our problem, our tutorial, our project problem. So what you can do is you can model your P of W given P in this way, and then the grammar will put the constraint that I will have W intersection W intersection W. So basically this will be, so this will give you uh, let's say W is a FSM. In your case, the digits example, W is an FSM which starts with a um, starts with a one. It's just an FSA, right? Because it is just accepting things, and it may have some weights. Let us say one is a weight of 1.5, 2. In your case, all these weights will be equal because uh, in your problem, these are all equal weights. 3, right? So this is the kind of FSM. Now to make the grammar, you can say I will have W, W, W. That's it. This is your grammar to be used in your three words recognition problem, right? W, W, W. So you will have either 1, 2, 3 or 115, 116, 2, 2, 3, like that. So this is your, for your tutorial, for your project. Only three words. And what is your W? Basically, W is a union of, this is simply a union of 1, comma 2, comma 3, etc., etc. Right? Okay. So just okay. I thought I will make it clear that how you will use that. Now, next is phonemes given the synonyms. So input is the synonyms and output is the phoneme. So how do you model that? Let's say if I have to say a word ka, then I will say this is the beginning point. I will say I will see a curve one, and I will output nothing. I will see a curve two, and again I will output nothing. And then I will see a curve three, and I will output curve symbol. Right? In a similar way, I can have let's say this is FST called curve. Then I can have FST called ver, na, ta, u. All these FSTs can be made, right? You know, this is very easy. Now, to make this probability P given D, you know, all these are possible. So you will take a union of all these. Na. You will take a union of all these. And then what you will do, um, basically closure, you have to apply closure, right? Because there are repetitions possible. So okay, no problem, just apply a closure on this. That's it. So you can have a ver followed by an a followed by an a followed by two, and that's how, since you are modeling with three states, so all of your individual FSMs will look like this. So ver1, ver2, and ver3, right? So the output will be ver if you see this sequence. So you see how easy, like, the FSM framework has made your task. You just define these things, and then you apply these very standard operations every time, and you construct more and more complicated words, grammars, etc. Okay, I think this is very easy. Now, what is left? We have got now something very important is coming up. probability of O given D. Yeah. Now, this is something you have to pay attention to. Are there any questions at this point? Sorry, I'm not checking the chat window. Let me go to the chat window. Are there any questions at this point? Any questions?
Sir, is it necessary to always go with three states?
No, it is not necessary, but that is the standard practice which everybody does. But people also use 5 states or they use triphones, etc. So yeah, 3 states is common, but you can use any number of states. Of course, if you have more number of states, then you will get more number of parameters. You require more training data. If you have less number of states, you will not be able to capture all the variability. So it's a kind of optimal. But yes, if you have more data, you can go for more number of states.
Sir, when we use acoustic features, like for example MFCC, and we say three states for ha,
Huh?
then does that mean like three different frames for ha?
Very good question. So very good question. I think we are that is our next topic of discussion. So right now we are discussing how are we mapping stenones to phonemes, right? This curve one is a stenone. Now many frames can correspond to one stenone. How do the frames are decoded into stenones? That we'll be discussing next. Okay, let's start with that now. So what we are discussing now is P of O given D, right? Yeah. P of O given D. So, given your C known, how do you model your MFCCs? It could be O given D or D given O. Basically, these are both equivalent because you can transform one into the other. O given D. Okay. O given D. Hmm. Okay. Okay. So what happens in your trellis, right? Okay. So until now, what we were drawing, these are all the HMM topologies, right? It tells you what sequence of states are possible. Now trellis is something which you actually observe, means which is basically trying to do the Vitabi decoding. Okay, it is something like this. You have some frames, MFCCs, right? Let me just take 3 for the sake of example, and let me take more, 4, 5. I think 5 should be good. Okay. Uh, Let me try to draw a possible topology, or not possible trellis. So let's say you are here, starting state, and you are observing. Now, what is here? We have here probability of D given O. Right? O is a single frame, D is a single synome. So D could be this. D could be either of, it belongs to the set. What set? Let's say R1, R2, R3, Ver1, Ver2, Ver3, Ner1, Ner2, Ner3, like that, right? There are so many synones possible. So my D is one of these synones. But what is the probability of this synone given? Now O is the MFCC at time t, at some at tth frame, right? So now this is the mapping which I want to do. What is the probability of the synone given the MFCC? Now you see here there will be a lot of variability because this we are using a Gaussian mixture model here, and uh, uh, many things sound very similar. Like when I say 7 versus 7, that means it's difficult to distinguish, but in real speech you do get a lot of variability. So Now, how do I model this? Okay, I will use arc to model each frame. So let's say this one. Let's say I will say from here to here. Uh, for R1, it has the weight. So what is weight in your trellis, in your Vitab algorithm? What is the weight? What is the weight you use? Negative log likelihood, right? Your weight is the negative log of that probability of D given O, right? So let's say the weight is 2, and for R1, for R2, the weight is something else, let's say 5. For I will just skip R and I'll go to some other phoneme, let's say ver. For ver1, the weight is, let's say, 7. For another phoneme like 2, let's say 2, 3, sorry, T3, the weight is something very large, 15 something, right? And then you make a next transition over this frame. Your AA1 is 3 and AA2 is say 4, and other things like ver is, let's say, large value 10, and T3 is again a large value 16. Then you make a next transition again, then you again make a next transition, then you again make a next transition. In this way you keep going. Now this is your entire trellis and you want to find the path which has the least weight. Now let us say here, if I go to, this is 2, this is 3, and how the weights are added, they are not multiplied, right? Because this is minus negative log, so you add them up, and finally whichever is the minimum weight, that is your accepted path, right? You add up all the weights along the path, right? And then the path with minimum weight, or let's say the paths, the top 3 paths or something, the paths with minimum weight, minimum accumulated weight, right? Accumulated weight are chosen, are basically selected, right? Where in you might output single path or you might output, let's say, top 3 paths, right? So now in this case, it is possible that is repeating many times. So, okay, now how do you handle this problem? Multiple frames may correspond to a single synone. How will you take care of that problem? So you have to take care of it here. Here you will say that my, let's say, let's come to feel free to ask any questions, and if you have, let's say I have one, 2, 3, and output is R. Okay. Now you see that you can have multiple like AA1, AA1. Then let's say AA2 is the least weight. Then somewhere here AA3 is the least weight. Then again AA3 is the least weight. And your output is AA. I mean basically the sequence AA1, AA1. So it's like this: AA1, AA1, AA2, AA3, and AA3. And you want to, this is your D given O, right? Then, but this will not be accepted by this transducer. This will not be accepted, right? So you have to apply a loop allowing one to repeat, allowing two to repeat, and allowing R3 also to repeat, right? Otherwise, you know that one state can extend to many frames. So basically, if you want to write it like in your, let's say one is one arc or one FST with a single arc, you will say one, then plus, because it can have, it should appear at least once, but multiple times are allowed. Then this is equal to R2, then a plus sign, then R3 and a plus sign, right? So that is your FST. It is composed of one FST with a plus closure, R2 with a plus, R3 with a plus, right? So similarly, actually will happen here as well. W1, khali, W2. Oh, I'm sorry, it should not be here. Otherwise, it's not deterministic, right? To make it, to keep it deterministic, I will add it here. Okay. See, in this way, I'm mapping my frames to words. Now I think that's it. We have covered all this thing, the whole mapping from starting from frames all the way up to sentences, right? Okay. Now I think what else? Yeah, there is a concept in like as I mentioned here that the weights are negative log likelihoods. So you may find in OpenFST toolkit there is a this discussion about how do we model these weights. They are modeled on a semi ring. It could be a regular semi ring or negative log semi ring or a tropical semi ring, etc. We use a tropical semi ring here. So in tropical semi ring, you have the functions. You have these functions basically: min function, negative log function. These are all part of tropical semi ring. If you wish, I can go into details of this, but I think you read it. You can also read it in the OpenFST toolkit. Tropical semi ring basically means that your operations are defined. That your um, to define a space, basically you need what do you need? You need a so basically a semi ring. A semi ring consists of a set of numbers or symbols, a plus operation. It's an operation. Multiplication. Oh, let me write it as multiplication operation, and concept of zero, that any element, if you apply this operation along, means if you take one element from here and the zero element and you apply this operation, then the output will be the same element, and then a one operation. So if you take any element from here, take one, multiply them, output will be the same operation. So in case of your regular semi ring, in your regular semi ring, these are all the real numbers, right? And plus is the normal plus, multiplication is the normal multiplication sign, and zero is the normal zero, one is the normal one. So basically, these are the concepts. These are concepts, and these are the actual numbers. This is the regular semi ring which you use in your normal calculations. So basically, when you have a graph, when you are uh, moving along a trellis, you are adding up all these entries, like it's one one, then the sum will become 1 plus 1 2, the weights are added. And similarly, the concept of multiplication, then you have, when you have two conflicting things coming over, you can multiply these two, right? No, sorry, I'm sorry, I made a mistake. So probabilities are getting multiplied, right? This probability of this into probability of this into probability of this, and when you are getting two things added up, then probability of this plus probability of this, right? So all these operations are generally on a regular semi ring, but we are not doing that way, because if we use probabilities, then it will become very small number, 0.00000, and you don't want to overflow your computers. That's why we are using log, and we are using negative log, and uh, for the Vitab scheme. So if we have a tropical semiring, then how does it look like? We have the element real, but we also have a notion of basically the real space union two symbols, infinity and minus infinity. These are two concepts that I will explain it a little now. Okay. Now, correspondingly, the this plus operation is replaced with a min operation, right? Because you know that when two branches are meeting, when two arcs are going to the same, you take the min operation and just choose one of them. Don't take both of them. Don't take a sum of both, but use a min operation. So plus is so that this operator is the min operation, and this multiplication operation, this is replaced by plus, because when you are going along the path, you're just adding them up. You're adding them up, and then you have so what is the correspondingly this symbol? So it should be such that if I apply this comma this, and if basically the min of an element x from the set, it's basically x belongs to this set, and comma this number, whatever number you will come basically 0. This should be equal to x, right? And what is that number? What is that number? Can anybody suggest? Minimum of x comma something is equal to x always for all values of x. What should be this? This should be infinity, right? Plus infinity. That's what you get, infinity. Now, you need this number here, that, what is that? If you do this into this, sorry, this into this, then you will get this only. So basically, your plus operation applied on x comma 1 bar should be equal to x. Or in other words, I say x plus 1 bar should be equal to x. What should be what is your x? What is your 1 bar then? This implies 1 bar equal to 0. This is your tropical semiring, which is basically used for Vitab decoding when you have negative log likelihoods as your weights. So right, I will just, this is simply to um, execute Vitab decoding with um, negative log weights. Okay, so yeah, there are other kinds of semirings possible for other kinds of operations. Like if you're not doing Vitab decoding, or if you're not using negative log weights, you may use other kind of semirings, but this is the most commonly used in ASR. Okay, I think it's time, and we can stop here. Any questions?
Sir, I have a question regarding the data class.
Pardon?
Sir,